Welcome to the deep dive. Today we're taking a close look at the global metamaterials technologies market.
That's right. We've got a 2025 report here, and it gives a really interesting snapshot of a market that's, well, it's already happening and growing fast.
Not just theoretical then, it sounds like it's already making waves, so to speak.
Exactly. This report shows it's generating real revenue now, and the projections for growth are pretty significant. It's about the here and now and what's coming very soon.
Okay, so maybe let's start with the basics for anyone new to this. What are metamaterials? Sounds very, sci-fi.
Yeah, they can sound that way. But think of it like this. Normal materials get their properties from their atoms, their chemistry.
Right, like metal conducts electricity, wood doesn't.
Exactly. Metamaterials, though, get their unique abilities from their engineered structure. Tiny, carefully designed patterns.
Engineer structure.
Yeah, smaller than the wavelength of, say, light or radio waves.
Yeah.
And because of that structure, they can bend light in weird ways or manipulate electromagnetic fields like nothing else can. Think invisibility, maybe, or super precise antennas.
Wow, okay. Sub-wavelength structures doing things normal materials just can't.
That's the core idea. It gives us this really fine-grained control.
Mind-bending indeed. So our mission today with this deep dive is to pull out the key insights from this 2025 report.
Yep. We want to understand the market size now, where it's headed, what's driving it, and where in the world things are really happening.
And the report gives us a good time frame, right? Base year 2024, looking back a bit to 2021, estimating 2025, and then forecasting out to 2033.
Correct. It provides that context, which is crucial for seeing the trends. Our aim is really to give you a clear picture, cut through the jargon.
And I gather there are some surprising applications we'll touch on, things like healthcare imaging, 5G, maybe even those cloaking devices you mentioned.
We'll definitely get into those. They highlight the real potential here.
All right, let's jump in. The numbers. What's the overall market size looking like for 2025, according to this report?
So for 2025, the global estimate is pegged at USD 824.67 million.
Okay, so a decent size already. But you mentioned growth.
Yes. The compound annual growth rate, the CAGR, is projected at 19.50% between 2025 and 2033.
19.5%. That's huge for a market already worth nearly $1 billion.
It really is. It signals significant expansion. By 2033, that growth rate implies a market size of USD 3,429.44181 million.
Over 3.4 billion, so nearly quadrupling in, what, 8 years?
Roughly, yes. That kind of trajectory definitely suggests we're moving beyond niche applications into broader adoption. Tends to attract a lot of investment, too.
What's fueling that? What's the main engine behind this growth?
The report points strongly towards the expansion of healthcare imaging and sensing applications. That seems to be a key catalyst right now.
Makes sense. Better diagnostics, better monitoring, always a huge demand there.
Absolutely. And metamaterials offer ways to potentially make those technologies smaller, more sensitive, or, just better.
Okay, let's look at the map then. Where is this market concentrated in 2025?
North America is reported as the leader, holding the largest share, over 37%.
Okay.
Now, here's something a bit odd in the report. It gives a regional market size for North America of USD 3073.93 million.
Hang on, 3 billion, but the global market was under 1 billion. That doesn't add up.
No, it doesn't. It's a clear discrepancy in the figures presented in the report itself. We have to flag that.
Right.
It could be down to how they define things regionally versus globally. Maybe different segments are included or excluded. It's not explained.
Okay, so we acknowledge the inconsistency in the numbers there, but directionally, North America is the biggest chunk.
That's the takeaway, yes.
Yeah.
The projected CAGR for North America is 17.3%. Within that, the U.S. is dominant, projected at $240.75 million for 2025 with a 17.1% CAGR.
Okay, that U.S. number seems more in line with the global total.
It does. Canada is estimated around $36.62 million, growing at 18.1%, and Mexico at about $27.77 million, growing at 17.8%.
Got it. So strong presence, despite the reporting quirks. What about Europe?
Europe's got the second largest share, reportedly over 29%. And again, we see a very large market size figure, USD 2,300 or 30.95 million for 2025.
Whoa, 23 billion. That's even more off compared to the global number.
Massively. So again, we have to treat that absolute number with extreme caution. It likely reflects a different calculation method within the report.
Understood. But the share, around 29%, and the growth?
The growth rate, the CAGR for Europe, is projected at 17.8%. So similar growth to North America.
And the key countries there?
The UK is estimated at $40.18 million, growing fast at 18.6%. France around $22 million, 17% growth. And Germany leads in Europe, apparently, with $47.35 million and 18% growth.
Okay, so significant activity in Europe too, but again, those big market size numbers are questionable based on the global total provided.
Precisely. It highlights the importance of looking at the relative shares and growth rates, maybe more than the absolute regional values given here.
Right. So where does that leave the Asia-Pacific region, APAC?
APAC holds around 24% of the market share, and its estimated market size for 2025 is USD 197.92 million.
Okay, that number fits much better with the global estimate of 824 million.
It does. And what's really striking about APAC is the growth rate. Its projected CAGR is 21.5%.
21.5%. So that's the fastest growing region globally.
According to this report, yes. It suggests really rapid adoption and investment happening there.
Why do you think that is? What's driving that faster growth in APAC?
Well, it's likely a combination of factors. You've got significant government focus on advanced tech in many APAC countries, plus a huge adaptable manufacturing base.
Right, it can scale things up quickly.
Exactly. And specific industries there, maybe consumer electronics or telecommunications, might be adopting metamaterials more aggressively.
Which countries are leading the charge in APAC?
China is the biggest player, estimated at $83.13 million in 2025, growing at 21%. Japan's next, around $27.31 million, 20% growth. And South Korea, close behind at $23.75 million, with 20.6% growth.
So China, Japan, South Korea driving a lot of that high growth.
They are, but the report also mentions good potential in India, Australia, Singapore, Taiwan, and Southeast Asia too, each with their own numbers.
Fascinating. So North America and Europe might have the biggest slices now, but APAC is really picking up speed. What about the other regions? South America, Middle East, Africa?
They have smaller shares currently, but still showing strong growth. South America is over 3.8%, around $31 million, growing at 18.5%. Brazil and Argentina are key there.
Yeah.
The Middle East has about 4%, nearly $33 million, growing at 18.8%. Saudi Arabia and the UAE are highlighted. And Africa holds around 2.2%, about $18 million, but with a strong CGR of 19.2%. South Africa is mentioned specifically.
So really, growth is happening everywhere, just starting from different bases?
That's a good way to put it. It's becoming a truly global phenomenon.
All right, let's dig into the different types of metamaterials the report talks about. It breaks them down, right?
Yes, it mainly focuses on two categories: magnetic metamaterials and photonic metamaterials.
Okay, magnetic first. What's the deal there?
These are engineered, like we discussed, but specifically to interact with magnetic fields. Think manipulating magnetism itself.
And the applications.
Things like advanced sensors,
Yeah.
really novel antenna designs,
Mm-hmm.
and yes, potentially magnetic cloaking concepts. Defense and medical imaging are big areas of interest.
Medical imaging, like MRI.
Potentially enhancing MRI, yes. Also emerging ideas in wireless power transfer and maybe even stealth technologies.
Magnetic cloaking. Still sounds wild. Okay, what about photonic metamaterials?
Photonic is all about controlling light. Again, using those tiny subwavelength structures.
Subwavelength structures interacting with light waves.
Exactly. This allows for things that are just, well, impossible with normal optics. Super lenses that see finer details than ever before, those optical invisibility cloaks you hear about, highly specific filters.
And where's the demand strongest for these?
Telecommunications is big, especially with 5G needing advanced components. Consumer electronics, too, think better cameras for displays. And even solar energy, potentially making panels more efficient. Miniaturization is a key driver here.
So one manipulates magnetic fields, the other manipulates light. Any other types mentioned?
The report briefly touches on acoustic metamaterials for controlling sound waves.
Ah, interesting. Noise canceling, maybe?
Or directing sound in unusual ways, potentially. And also chiral metamaterials, which have unique reactions to polarized light. But the main focus seems to be magnetic and photonic right now.
Got it. Okay, so those are the types. How are they actually being used? What are the big application areas?
The report identifies medical devices as the fastest growing application segment.
Fastest growing. We heard healthcare was a driver. What kind of devices?
Enhancing imaging, like MRI, like we mentioned. Developing smaller, better antennas for things you might implant in the body.
Implantable devices.
Yeah. And creating really sensitive, non-invasive biosensors. Think wearable tech for health monitoring.
Wearable sensors using metamaterials? That could be huge for preventative medicine.
Absolutely. The demand for portable, wearable electronics in healthcare is definitely pushing this.
What other major application areas are there?
Sensors more broadly are key. Metamaterial sensors can be incredibly sensitive and tunable.
Tunable, meaning you can adjust what they detect.
Precisely. They can be designed for electromagnetic fields, sound, heat, chemicals. Very versatile. So healthcare monitoring, yes, but also environmental sensing, checking air quality, or industrial diagnostics, maybe detecting tiny flaws.
And the report specifically mentions biosensors again.
Yes, highlighting their potential for detecting disease markers really early at very low concentrations. That's a major goal in diagnostics.
Game-changing potential there, beyond medical and general sensors.
Optics and antennas are also called out as key areas, which lines up with the growth in photonic metamaterials for lenses and filters, and magnetic or other types for better antennas.
Antennas for what? 5G satellites?
Both, and more. Making antennas smaller, more efficient, able to steer beams electronically. That's crucial for modern communications.
Okay, so we have the types, the applications. What are these things actually made of? What materials go into them?
The report focuses on metals and dielectrics as the main ones.
Metals like.
Copper, silver, gold sometimes. Conductive elements. They're really good for manipulating electromagnetic waves, especially at higher frequencies.
So for things like radar and communications, cloaking.
Exactly. Antennas, sensors, cloaking concepts often rely on metallic structures.
And dielectrics, what are those?
Those are non-conductive materials. Think ceramics, polymers, certain types of plastic.
And their advantage?
They tend to have lower signal loss,
Mhm.
especially at optical frequencies for light. So they're great for lenses, photonic crystals, advanced imaging stuff. Plus, they often handle heat better than metals.
Better thermal stability. Right.
The report also gives a quick mention to superconductors as a possibility, but doesn't go into detail.
Metals for EM waves, dielectrics often better for light and heat. Makes sense. Now, how do you actually make these incredibly detailed structures? It sounds difficult.
It is complex. The report mentions two main approaches, top-down and bottom-up.
Top down, like carving.
Sort of, yeah.
Yeah.
Think microchip manufacturing. You start with a larger piece of material and use techniques like lithography, like printing a pattern, and etching to remove material very precisely, creating those nanoscale features.
Okay, high precision. Good for.
Really complex electromagnetic designs, especially for photonics or terahertz waves, where the structures need to be incredibly tiny and accurate, specialized devices like advanced sensors or maybe those cloaking demonstrators.
But maybe expensive or hard to scale up.
That can be the limitation, yes. Cost and scalability, especially for large areas.
So what's the alternative, bottom up?
Bottom up is more like building from the ground up, molecule by molecule almost, using things like self-assembly where materials are designed to automatically arrange themselves into the desired pattern, or chemical synthesis.
Self-assembly, that sounds efficient.
It can be, yeah. It often holds more promise for scalability and lower cost, making it attractive for things like flexible electronics, maybe some acoustic devices, or energy harvesting applications where you need large areas.
But maybe less precise than top down?
Traditionally, yes, achieving that ultra-fine precision was harder. But, nanotechnology is always advancing, blurring those lines.
Fascinating. Two very different ways to build these things. Okay, who's buying all this? Who are the end users?
Aerospace and defense is a big one, and it's growing.
Why them?
Those unique electromagnetic properties are really attractive. Radar self, obviously. Better antennas on planes, drones, satellites. More secure communications.
High-stakes stuff, driven by military spending.
Partly, yes. Investments in next-gen defense tech and also the expanding commercial satellite industry are definitely drivers.
Okay, who else? We talked about healthcare already.
Healthcare is definitely a major end user, yes. Not just the device makers, but potentially hospitals and diagnostic labs using technologies enhanced by metamaterials. Think better MRI scans, those advanced biosensors we mentioned, maybe wearables for continuous monitoring.
Right. And telecommunications.
Telecommunications is another key one mentioned, mostly driven by the need for better antennas for 5G rollout and looking ahead to, 6G and beyond.
So a pretty diverse customer base already. Aerospace, defense, healthcare, telecom. What are the big picture forces pushing this market forward? The drivers.
The report highlights a few key things. First, just the ongoing improvements in nanofabrication making these things is getting easier, cheaper, more scalable. That's huge.
Right, the manufacturing piece.
Second, the growing uptake in those high-value sectors like aerospace and defense really pulls the market along.
Creates demand, funds R&D.
Exactly. And third, those big global investments in 5G and future wireless systems are creating a clear need for the kind of components metamaterials can enable.
Powerful drivers. What about the flip side? Any major roadblocks or restraints mentioned?
Two main ones are flagged. One is regulatory uncertainty.
New technology, unclear rules.
Yeah, especially for novel applications. If the rules aren't clear, it can slow down commercialization, make companies hesitant.
Makes sense. And the other?
High R&D costs. Developing these materials and figuring out how to integrate them is expensive. That can be a barrier, especially for smaller companies trying to get in.
Standard challenges for cutting-edge tech, really. Regulatory hurdles and the cost of innovation. Are there any specific trends within metamaterials that the report points out as being particularly hot right now?
Yes, a couple of interesting ones. First is the rise of metasurfaces.
Metasurfaces, like 2D metamaterials.
Exactly. Ultra-thin, flat versions. They're making waves in optics, allowing for incredibly thin, lightweight lenses and other components. Think flat lenses for cameras, VR headsets, sensors.
Oh, replacing bulky curved glass.
Potentially, yes. Very exciting for miniaturization. The second trend mentioned is topological metamaterials.
Topological. That sounds mathematical.
It kind of is. It's about materials designed with special properties based on topology,
Oh.
which makes them really robust. They can guide waves, light, sound, whatever reliably, even if the material has defects or imperfections.
So signals don't get easily scattered or lost.
That's the idea. Really promising for reliable communication or sensing in noisy or difficult environments.
Metasurfaces for flat optics, topological materials for robust waves. Cool. Okay, last piece. Who are the companies actually doing all this? What's the competitive scene like?
The report describes it as dynamic, very competitive, lots of innovation happening quickly because the demand is growing across so many areas.
Any specific names mentioned?
Yeah, it calls out players like Hymeta Corporation. They do flat panel satellite antennas, Ecodyne, known for metamaterial radar, Metamaterial Inc., now called Metamaterials, working across various applications, and Lumotive, focusing on beam steering for LiDAR.
So companies specializing in different applications.
Right, developing things like those steerable antennas, advanced imaging, maybe even working on those cloaking ideas. But it also stresses the importance of startups and university spin-offs.
Ah, the innovation engine.
Exactly. Often backed by venture capital or government grants, they're pushing the boundaries alongside the bigger players. It's a real mix.
Sounds like a very active space. Well, this has been fascinating, really getting under the hood of the metamaterials market with this report. Let's try and quickly sum up the main takeaways for you listening.
Yeah, absolutely. I think the big picture is clear. This market is set for really significant growth over the next decade or so.
Almost 20% a year projected.
Right. Driven strongly by healthcare, needs better imaging, sensors, but also major activity in aerospace, defense, and telecoms.
And we're seeing diverse applications pop up, from manipulating light for flat lenses to potentially even manipulating magnetic fields for stealth.
Exactly. And while North America and Europe are big markets now, APAC is growing the fastest, showing really rapid adoption. Plus, the technology itself is evolving fast, with things like metasurfaces and topological materials opening new doors.
And the aha moment for me is just realizing how fundamentally different these materials are. Engineering structure to get properties,
Yeah,
it really changes the game.
it does. It's moving beyond just finding new substances to actively designing material properties at a micro level. The potential is immense.
Which leads to that final thought, maybe for you to ponder. How will this ability to engineer materials fundamentally reshape the tech you use every day?
Yeah, think about your phone, your car, medical checkups in the future. Where might these invisible engineered structures pop up? What new things become possible when we can control light, sound, and electromagnetic waves with this level of precision?
It really opens up the imagination, doesn't it? What disruptions, what new possibilities lie ahead? Definitely a field to keep a close eye on.
For sure. The innovation isn't stopping. It's going to be an exciting journey to watch.
Indeed. Thanks for joining us for this deep dive.